Let's investigate ancient examples of the Affine cipher, which is a type of monoalphabetic substitution cipher. In this video, we will uncover the hidden meaning behind these two cryptograms. We will be using the 22 letters of the Phoenician alphabet. The Phoenician alphabet includes Aleph, Bet, Gimel, Dalet, He, Waw, Zain, Het, Tet, Yod, Kaf, Lamed, Mem, Nun, Samek, Ain, Pe, Tzadeh, Kof, Resh, Shin, Tau. So these 22 letters can be split into two groups of 11. And I've purposefully written them in this way so that we can easily use the ATBaSh cipher. We'll be using that later in this video to figure out what these two cryptograms are telling us. You can find counterparts in the modern Latin alphabet for most of these letters. So here we can see A, B, C, and G, D, E, F, and Y, and U, and V, and W. All of those letters can be traced back to Waw. And over here we can see Z, H. Now this Tet does not have a counterpart in the Latin alphabet, but its counterpart in the Greek alphabet is Theta. Then Yod has two counterparts in the Latin alphabet, and they are I and J. And here we have K, L, M, N. Samek has a counterpart in the Greek alphabet, and that is Xi. Then over here we can see O, P, and we can skip Tzadeh, and then we have Q, R, S, T. So most of these letters, they do have a counterpart in the modern Latin alphabet. Now let's introduce the Affine cipher, and then we're going to see several examples of the Affine cipher using these 22 letters in the Phoenician alphabet. So we need to define X, Y, A, and B. And these are all elements of the integers mod n. N is the number of letters in the alphabet. So for this case, we're dealing with n equals 22. Let's define the encryption function. So the encryption function is going to take an input, x, and it's going to map it to a times x plus b mod n. So n is the modulus. We are working with modular arithmetic. So this is the encryption function. And now let's have a look at the decryption function. The decryption function is going to take in the input y, and it's going to map it to the multiplicative inverse of a. We can write that as a to the power of minus 1. So this is the multiplicative inverse of a mod n. And then we're going to multiply that by the input minus b. And this is all done mod n. Now, we need there to be a multiplicative inverse for a. And that's why we need to impose a special condition between a and n. The greatest common divisor of a and n must be 1. Or in other words, a and n must be co-prime. And that allows us to compute this multiplicative inverse mod n. And then we can perform decryption. So we can encrypt and we can decrypt. So this is the general description of the Affine cipher. And it is a type of monoalphabetic substitution cipher. So x and y, they can take on any of these values, 1 through to 22. But because we are working mod 22, n is equal to 22, that means that 22 is the same as 0. And we're using the specific convention where we start numbering from 1. So Aleph is numbered with 1, Bet is numbered as 2, Gimel is numbered as 3. Alternatively, we could use another convention where we start counting from 0. Then we would have 0, 1, 2. But for this video, we're going to stick with this convention. So Tau, which is the final letter in the Phoenician alphabet, it is 22, or we can think of this as 0. So 0 is the additive identity. Now, let's consider the case where n is equal to 2 times 11, or 22. So here we have 22 letters in total. We're going to consider these 5 examples. So first, let's consider the example that is called AShBaR. Now, what does this name tell us? AShBaR tells us that we have Aleph, Shin, and then we have BaTGaSh. So Aleph, Shin, BaTGaSh. It's telling us that 1 is paired with 21 and 2 is paired with 20. These are additive inverses. 1 plus 21, that's 22. 2 plus 20, that is also 22. And 22 is the same as 0. So this is the same as having the situation where we have A equals -1 and B equals 0. So there's no shift over here. B is 0. And what we're doing is just negating the input. And that is the same as finding the additive inverse mod 22. So that's this first example. And it's given the name AShBaR. So note that we're reading from right to left. Let's have a look at the next example. That corresponds to B equals 1. So here we have A equals -1 and B equals 1. So this one is called ATBaSh. ATBaSh, that's telling us that we have Aleph, Tau, Bet, Shin. So 1 is paired with 22, 2 is paired with 21. And this is the cipher that we need to use to uncover the hidden meaning of these two cryptograms. So that corresponds to A being -1 and B being +1. And we need to compute this mod 22. And let's also have a look at this example over here. This one is called BaTGaSh. So we have Bet Tau and then Gimel Shin. So we have Bet Tau, Gimel Shin. 2 is paired with 22 and 3 is paired with 21. So that corresponds to B equals 2. So for these 3 examples that we have just looked at, for all of them, we have A equals -1. And we're just changing this value of B. So we have B equals 0, B equals 1, and B equals 2. Now, because we have this value of -1 over here, the encryption function and the decryption function are the same. Now, why is that the case? It's because -1 times -1 is the same as +1. So -1 is its own multiplicative inverse. So both A and A inverse are the same. We have -1. And this minus sign over here and this minus sign out here will cancel, and then we'll be left with +b. So if we have -x plus b, it's exactly the same here with a decryption function. So both encryption and decryption are going to be exactly the same. And that means if you apply the encryption function twice, it's going to be the same as not applying anything at all. It's going to be the identity function. You're just mapping x to x or y to y. You map the input back to itself. So that is a very interesting property for these 3 examples. Now let's have a look at these last 2 examples down here where A is +1. So over here we had -1, now we have +1 for A. This example over here is called ABGAD. So Aleph, Bet, Gimel, Dalet. So here we have Aleph, then we have Bet, and then Gimel and Dalet. So what is that telling us? Aleph goes to Bet, Gimel goes to Dalet. 1 goes to 2, 3 goes to 4. So it's a linear shift, we're just adding 1 to this number. And that's why we have b equals 1. So over here, it would just be x plus 1. We're just shifting it by 1. Now let's have a look at this final example. Here we have al-bam. Al-bam is aleph, lamed, bet, mem. So aleph, lamed, bet, mem. We're mapping 1 to 12 and 2 to 13. That means we're adding 11. 11 is half of this modulus. Now this is very special because 11 is its own additive inverse. So 11 plus 11 is 22, and 22 is the same as 0. So that means the encryption and decryption functions are the same for this final example, al-bam. But that is not the case for this one, ABGAD. For this one, where b is equal to 1, if you want to decrypt, you have to put a minus sign in front of that 1. So here you have plus 1, and over here you have minus 1. So if you want to go from aleph to bet, and then decrypt, you have to go from bet to aleph. So you have to reverse. But because over here we have b equals n on 2, it's a very special case. If we start with aleph, and then we go over here, we add 11, and we're at lamed, and then if we add 11 again, we're going to be back to aleph. So applying it twice is the same as not applying anything at all. Encryption is the same as decryption. So that is not in general true. It's true for these 3 examples, and it's true for this last example, but it is not true for this ABGAD example. So for a equals plus 1 and b equals plus 1, it is not true. You have to change the sign over here when you define the decryption function. So now that we have seen these examples, we can go over here and we can do some decryption. So we're going to use the ATBaSh cipher. That is this second example. So ATBaSh corresponds to a equals minus 1 and b equals 1. So that is this one over here. So what we need to do is identify shin, shin, kaf. So first, let's have a look at shin. So shin is over here. It is 21. Shin is paired with bet. So we can change this over here, and we can call this bet. So we have shin goes to bet. And this is also shin, and this goes to bet. And now let's have a look at kaf. So kaf is paired with lamed. So we need to put lamed over here. So we have bet, bet, lamed. So we can read this word up here, we can read that as shishak. So we have shishak, and underneath we have babel. Shishak gets mapped to babel when we use the ATBaSh cipher. And babel, that means Babylon. So we can write this as Babylon. We have the word Babylon. So Babylon is written as bet, bet, lamed, Babel. And this shashek over here, that is the ciphertext. So we can think of this as the ciphertext, and this is the plain text. Now let's do the same for this cryptogram over here. So here we have lamed, bet, kof, mem, yod. We could read this as leb kamai. So what is leb kamai hiding? What is the hidden meaning of leb kamai? So lamed is paired with kaf. So we can write kaf over here. Bet is paired with shin. So we can write shin over here. Kof is paired with dalet. So we can write dalet. Mem is paired with yod. So mem and yod are pairs. And here we have mem yod, so we're going to have yod mem. So we have yod and then mem. And this can be read as Kasadim. Kasadim is referring to the Chaldeans. So we have the Chaldeans. So we figured out the hidden meaning of these two cryptograms. So Sheshek means Babel, which is Babylon, and Leb Kamai means Kasadim. Kasadim means Chaldeans. So we worked out these two cryptograms. Now, for all of these examples, we have been dealing with n equals 22. But what if instead we used the modern Latin alphabet? Then we'll be able to define the Caesar cipher. So let's do that over here. The Caesar cipher is also a type of affine cipher. And just like these two down here, the Caesar cipher has A equal to +1. And if we want to use the Caesar cipher with the modern Latin alphabet, then we can use n equals 2 times 13, which is 26. So this is assuming that we're using the modern Latin alphabet, where I and J are treated as distinct letters, and U, V, and W are all treated as distinct letters. So that's the modern Latin alphabet, which has 26 letters. And you can see, again, we have an even number, so we can arrange them into two groups. And there's actually a special case of the Caesar cipher, which is referred to as ROT13. And this is a very special case because 13 is 1/2 of n. So we're again dealing with the case where B is equal to n on 2. So ROT13 is a special type of Caesar cipher where encryption is the same as decryption. So 13 plus 13 is 26, and if we're working with this situation where it's modular arithmetic mod 26, then 26 is the same as 0. So if you add 13 to an entry, then you just have to add 13 again, and you get back to where you started. So encryption is the same as decryption for ROT13. But in general, this is not the case for a general Caesar cipher. So you can see that these two can actually be thought of as Caesar ciphers, but we're only using 22 letters in the alphabet because this is a Phoenician alphabet, and over here we're using 26 letters. So all of these are types of affine ciphers. And affine ciphers are a type of monoalphabetic substitution cipher. And you can see that there are several potential weaknesses if we use a monoalphabetic substitution cipher. If you look over here, we have shin and shin. They both get mapped to the same letter. So from that, we can infer that we had the same letter over here. And the ATBaSh cipher, it does look very interesting, and it's a very nice pairing of letters, but it is not very good at securing information. So for modern cryptography, we don't use these types of monoalphabetic substitution ciphers if we want to protect information. But this is important in the history of cryptography. So this type of mathematical operation, which is done with alphabets, that is the precursor to modern cryptography. And we wouldn't have modern cryptography if we didn't have this historical background that underpins mathematics and also allows us to write. So this is the written word, which really allows us to communicate our ideas and accumulate knowledge. So this is an essential entry into the history of cryptography. So now you know the hidden meaning behind these two cryptograms. Sheshek means Babel, which is Babylon, and Leb Kamai means Kasadim, which is the Chaldeans.